And sorry again for the delay. And let me start now. My talk today is about exploring the ultraviolet from neutrino oscillations and effective in the EFT framework. This talk is based on our two recent papers shown here. To start, we have heard many talks today and yesterday on the connection between SMEFT and the LGC. So tonight, I would like to move your eyes slightly to a lower energy regime, where we also have various precision experiments like parity violating electron scattering experiments, neutrino oscillation experiments, and precision cosmology, etc. Tonight, I would like to focus on these two kinds of low energy experiments. To be more specific, I will only focus on neutrino non-standard interactions from an EFT approach. The neutrino non-standard interaction could generically be classified into two categories, the charge current NSS and the neutral current NSS. For the charge current NSS, I will study the effects from DIM6 SMAP operators on the terrestrial neutrino oscillation experiments based on this work. Well, for neutral current NSS, operators up to dimension 7, I will study their impact on ineffective, meaning the effective number of relativistic species in the early universe based on this paper. Before going to the details, let me briefly introduce our main findings. And for the charge current NSS, we find long baseline neutrino oscillation experiments are currently reaching the 20 TeV scale in terms of new physics. Well, for neutral current NSS, we find precision measurements of ineffective are currently sensitive to new physics at around 200 G. Now let me go into some details, and let me start with the charge current NSS. In practice, neutrino oscillation experimentalists are mirroring the mismatch of neutrino flavors between production and detection. The effects of new physics are usually parameterized using the so-called production and detection parameters in the quantum mechanical framework. Using the wealthy data currently available from neutrino oscillation experiments, we can obtain the upper bounds on these operator parameters as listed in this table. And from the second column, you can see that the current upper bounds on these parameters are already at the percent or even milli level. Similarly, as we can utilize electroweak precision observables and the LGC data to indirectly probe new physics. We ask ourselves a similar question. And the question is as follows: what is the implication on the UV physics from the very stringent upper bounds on these production and detection parameters? So to answer this question, perhaps as particle physicists, we are more familiar with the Lagrangian language in the QFT framework. Since the neutrino oscillation experiments are performed at a very low energy scale, the system can be described by this effective Lagrangian, where the effects of new physics are encoded in this epsilon L, epsilon R, epsilon S, epsilon P, and epsilon T parameters, which are usually called the NSI parameters in the QFT formalism. Now, if we want to transfer the upper bounds on this production and detection parameters as we showed in last slide onto those of the NSI parameters in the QFT formalism, we have to first find a connection between these two frameworks in the first place. A consistent matching between these two formalism was not obtained until recently in this paper by Fokoski et al. I will now discuss the technical, very lengthy calculations to obtain the matching. But if you are interested, we can. I can tell you the details to. For the calculation. Now, if you have after you have performing the consistent matching, the production and detection parameters can be expressed as a linear combination of the NSI parameters, as you can see here. Now, using this matching formula, you can easily translate the upper bounds on these parameters onto those of the NSI parameters. This is shown pictorially here in this slide. Now at this stage, the question we can ask ourselves is how would you generate these non-standard interactions? Since we are interested in a more independent study, we could start from some EFTs as some scales and to systematically list the independent and complete operator basis. I refer you to John Howe's talk as well as Chris' talk earlier today. To our purpose, we just assume we have some unknown UV physics at some scale lambda above the weak scale in W. Now, if you, since we are interested in our model independent study, you have to first perform a matching between the UV physics and the EFT at this scale, which would be the SNAP framework. This matching, I'm not going to discuss how to do the matching, but if you're interested, you can refer to Xiaotran's talk and Josep's talk earlier today. Now, at this scale, the SNAP framework will serve as an ideal framework for our purpose in order to study the potential new physics model independently. But as you already noticed, there's an energy gap between SNAP and the neutrino oscillation experiments. So you have to perform a multiple step matching and running in order to transfer the lower bounds, the upper bounds on these NSI parameters onto the lower bounds on the UV scale lambda in the SNAP framework. Using the current neutrino oscillating data, we obtain, and after performing a scan over all the SNAP operators, we show our result in this plot, where the Y is the scale of new physics in TV, and the x-axis labels the SNAP operators. The orange is for diode, and the cyan for double choose, and green for random. The blue is for combined analysis of these three types of reactor neutrino oscillation experiments. And from the y-axis, you can conclude that these reactor type neutrino oscillation experiments are currently approaching the 5 TeV scale in terms of new physics. And we have performed a similar study for long baseline neutrino oscillation experiments, and the results are shown in the lower panel, in the lower plot, where again the Y is the UV scale lambda in TV and X are the SNAP operators. And you can, from the y-axis, you can read that the long baseline neutrino oscillation experiments are approaching the 20 TeV scale for the new physics. Now, if you compare the y-axis of these two types of neutrino oscillation experiments, you may naively conclude that the long baseline neutrino oscillation experiments are doing much better than the reactor type neutrino oscillation experiments. However, we want to stress that this is not the full story, and the reason is as follows. If you look at this, for example, 3 operators circled in blue, you can see that the reactor type neutrino oscillation experiments can constrain them around 40 eV. However, the long baseline neutrino oscillation experiments are not sensitive to these 3 operators at all. So in this sense, we say that the long baseline neutrino oscillation experiments and the reactor type neutrino experiments are complementary to each other, meaning they are sensitive to different subsets of the SNAP operators. Okay, now let me move on to the neutral quantum NSIs. Last time when I showed this plot, I mentioned that the charged quantum NSI could be induced by some UV physics after you perform match and running shown here. However, at this point, you could also have some neutral quantum NSI from some UV physics. And for the neutral quantum NSIs, the Lagrangian is usually parameterized this way as shown here, where if you parameterize the effects of some new physics, alpha, beta as the flavor indices of neutrinos, F is either the electrons or the first generation quarks, P is the projection, the chiral projection operators. In the quark case, meaning when F is the first generation quarks, this scenario has been extensively studied in literatures. For example, the coherence experiment, LSNDX, taxono, Charm2 lab, and Munu, etc. In the future, Dune will become an even more powerful tool in searching these neutral kind of ISIs. Well, in the electron case, meaning when the fermion is an electron, these neutral kind of ISIs have only been studied in the case where we have, in the case of long baseline neutrino oscillation experiments, where the matter effects become significant. In this talk, we want to provide a different angle in understanding this neutral kind of ISIs, which is done as follows. So in the early universe, when you introduce interactions between neutrinos and electrons, you could modify neutrino decoupling in the early universe, which will in turn predict different numbers for an effective. However, we know that an effective has been precisely measured by Planck and would be even more precisely measured in the future by CMBS4. So at this point, the question we ask ourselves is how neutral kind of ISIs would affect neutrino decoupling in the early universe. Now, to answer this question, we did not constrain ourselves to dimension 6 neutral kind of operators. Instead, we consider all possible operators up to dimension 7 as listed in this table. For future convenience, let me emphasize that 016 here stands for the vector type interaction, while 026 for the axial vector type interaction. Since this is an EFT workshop, we are not interested in any UV completion of these operators. But let me briefly mention that, for example, for the contact interaction between neutrinos and electrons, these operators could be induced by some U1 prime models. While for the neutrino self-interacting operators, we could obtain this kind of operators by, for example, the Majorana model. Now, each operator in this table would introduce accurate corrections to particle scattering or annihilation in the early universe, thus modifying the prediction of ineffective. Now, to quantify the correction of this BSM physics, which is encoded in the collision term, you only need to solve the Boltzmann equations shown here. The first one is for the number density. The second one is for the energy density. However, this is a differential integral equation, and on the right-hand side you have a 12-fold integration to do, which makes these Boltzmann equations very difficult to solve. But don't worry, in our recent paper, we have provided you a complete generic and analytical dictionary for these collision term integrals. By collision term integrals, I mean the 12-fold integral for the collision term on the right-hand side of the Boltzmann equation. So using our dictionary, these Boltzmann equations become trivially solvable. So now applying corrections from those operators, we show the constraints on the UV scale in this plot, where the y is the UV scale lambda in GeV, and the x-axis labels the operators we consider in our paper. The first two cases correspond to the aforementioned vector and axial vector type neutrino electron contact interactions, and you can see that precision measurements of any effective are currently sensitive to any potential new physics around 200 GeV from the vector type interactions. On the other hand, the vector type interactions are more constrained compared with the axial vector case, and the reason is simply that the vector type contact interactions interfere with some model corrections constructively, while that for the axial vector type interactions destructively. Now, if you look at the dimension 7 operators, these operators are relatively weakly constrained compared to dimension 6 operators. Even though the current upper bound, lower bounds are very small, we want to stress that this for most of these operators shown here, our work represents the first study on these operators. Now, as I mentioned earlier, there are lots of experiments looking at this neutral kind of NSS. You may already have this question: how would our results compared with previous results on this neutral kind of NSS? And to make the comparison, we have to first transfer our notation into those usually used in literature as shown here. After doing the conversion, we show we list the constraints on these evaluation parameters in this table, where this column stands for a global analysis of existing neutrino oscillation data plus the coherent experimental data, and those intermediate data correspond to the constraints from previous collider experiments. And this column corresponds to the prospects from Dune using different exposure, and the last column corresponds to our work, whereas the first column corresponds to that from Planck, and the last corresponds to that from CMBS4. If you compare our numbers with previous ones for the Planck, you can see that the constraints is relatively weaker than existing ones. However, when you look at the the constraints from CMBS4, you can see that especially for those underlined in blue, the constraints from CMBS4 are comparable or even stronger in some cases. So in this sense, we say that precision measurements of ineffective are complementary to other type of experiments in constraining neutral kind of assays. Now let me go to my conclusion. In this talk, I have discussed the neutrino non-standard interactions, and I have first discussed the charge kind of assays. We found that reactor type neutrino oscillation experiments are sensitive to different subsets of SMAP operators compared to the long baseline neutrino oscillation experiments. And for the long baseline neutrino oscillation experiments, we found that they are already sensitive to new physics at the 20 GeV scale. For the neutral kind of NSS up to dimension 7, we considered constraints from precision measurements of ineffective from Planck and the proposed value of CMBS4. We found that CMBS4 would be complementary to other types of neutrino experiments like coherent collider or other oscillation experiments. That is all I have for today, and thank you for your attention.
Thank you very much. Are there any questions? We do have time. You can raise your hand, write in the chat, open the microphone. Otherwise, I actually have a lot of questions, but I see Ken has one, so please.
So these other constraints that you mentioned, I guess they come from what, like LEP or solar constraints, or what?
Oh, you mean collider constraint on the neutral kind of NSS? Yes, we have LEP CHAM2. Actually, we have lots. It's a summary, so we have listed all previous collider experiments like LEP you mentioned, CHAM2. As listed here, we have OPO. This is actually LEP. Yes, all kinds of previous collider experiments.
I see. Thanks.
And so you keep quadratic terms when you do these calculations, or you do truncated interference level? How does that work?
Do you mean the neutral kind or charge kind case?
Both of them actually, but I was thinking like, so for the neutral, I actually had a question that is about, so you're considering both dimension 6 and dimension 7, right? So how do you play with those, and does it matter the dimension 7 violet lepton number, for instance?
If you look at the Grange, the operators, the dimension 7s, it varies the lepton number by 1, since we assume a Majorana neutrino. If you compare the difference between Dirac neutrino, it's only a factor of 2, and we don't find any visible effects on violating lepton numbers for these operators. And for your previous question on the interference, for the neutral Kant ISS, we kept both the interference term with the standard model corrections as well as the quadratic correction from these operators. For the charge current ISS, there's no interference because there's no square thing. So there's no such interference. Yes.
Okay, that makes sense.